Okay, we are back for part 2 of earthquakes. I was just wondering if anyone's had a chance to watch San Andreas yet. That was your extra credit assignment for over the first few weeks of quarantine. Anyways, hopefully you noticed some of the fabrications or sensationalizations that Hollywood put into that. And the things that were scientifically valid. Anyways, we'll continue on with locating and measuring earthquakes. We're talking about measuring now the size of the earthquake. And so we'll first look at intensity, and that's the measure of the effects an earthquake produces. That's both on structures and people. And it's a bit subjective. Think back to last summer when we had an earthquake. A decent size. Well, we didn't have one. Ridgecrest in that area had one, but we definitely felt it. And as you talk to people, their perception of how big or how long the earthquake lasted was probably very, very different. Even though we all experienced the same earthquake, some of it had to depended on where we were at. Some of it just depended on our perception and how we viewed what was going on. One time I was getting my eyes checked, and I was at the eye doctor waiting for the doctor to come in, and I was sitting in my chair, and all of a sudden I heard all this clanking, and I'm like, what's going on? And then I started noticing the door moving. I'm like, oh wow, we're having an earthquake. And about the time I was looking around and figuring out where I'd go for safety, before I even got up out of my chair, it was already over. And as it was happening, I looked at my watch to see how long it was lasting, and it probably was maybe about 15 to 20 seconds at the very, very most. But when I left my appointment and talking to the office ladies in the front, the way they made it sound, it was, the biggest earthquake, probably something similar to what was in San Andreas. And it lasted for well over a minute. So obviously when people feel things, depending on how maybe frightened they are, it has an effect on how they view it. So anyways, the modified Mercalli scale has a range of 1 to 12. Some of the drawbacks are that damage lessens with distance from the epicenter. And so, the accuracy, it's not as accurate, I should say. And it also depends on several other factors, like the type of geology, the rocks, the construction of the buildings. For instance, if we have an earthquake in LA, where buildings are built to withstand earthquakes, compared to a giant earthquake in, say, the Midwest somewhere, there's going to be a lot more damage because the buildings aren't built to the same codes, because they're not expecting big earthquakes. Or you go to a third world country where they do not have the infrastructure to build, newer up-to-code earthquake-resistant structures. And when they have an earthquake, even though it might be a lot smaller than one we would experience, they have a lot more damage, destruction, and loss of life in areas like that, or injuries. All right, magnitude gives us a lot more precise way of measuring an earthquake, and that measures the amount of energy that's released by the earthquake using the amplitude of seismic waves at a seismogram. So Richter scale is a numerical scale of magnitudes. It was originally developed for shallow earthquakes in California. You'll still sometimes hear Richter scale used by news people just because that's what they're used to saying, even though the numbers and information that they get is generally probably moment magnitude, but a lot of times they get used interchangeably. For moment magnitude scale, it's a much more objective measure of the energy released. It uses 3 main factors. It uses the strength of the rock, the surface area of the fault rupture, so the area along the surface that there was that movement, and then how much movement occurred. And taking those 3 things, we're able to get a lot more accurate measurement of the energy released by an earthquake. So there's a graph over here with some, that's what I'm looking for, notable earthquakes, different sizes, and approximately how many of that magnitude earthquake that we have. So you can see something that's in the 9 range, we have less than one of those per year. But notice the amount of energy released by this earthquake compared to the energy released by, say, a 3. You know, when we felt the earthquake in Ridgecrest last summer, we were feeling probably somewhere about a 4 roughly, maybe 4.5 if I remember right. But look at the amount of energy released in Ridgecrest, where it actually took place. I forget the actual number off the top of my head, but I think it was right about at 7. So notice we're at 1.8 billion compared to our less than 1.8 million. So a substantial difference is an exponential curve of the energy released by an earthquake. So the difference between a 4 and a 5, look at that amount of energy, substantial. And the difference between a 5 and 6, but look at the difference between a 7 and an 8. You know, 7's scary, 8's like straight up super scary, and a 9, that's a big deal. So take note of that and keep that in perspective when you're hearing magnitudes of earthquakes and how big they are, and kind of keep that in perspective for the earthquakes that we feel here in Bakersfield on occasion. So earthquakes are most common, obviously, in the western states. We can see where our highest hazards are. But, you know, we even have some high hazards in through here. And then up in Alaska, very tectonically active. The largest seismic risks or hazards exist near plate boundaries, so along the Pacific coast. And when we get to plate tectonics, we'll look a lot more at that and how we use earthquakes to map those boundaries. And seismic risk is determined based on the assumption that large future earthquakes will occur where they have occurred in the past. So we look at this seismic gap. I don't know if I have, I don't think I do. But for instance, here along the San Andreas and this particular area, we know that every so often, I think it's about 150 years or so, we have a major earthquake occur. And so we can look through the geologic record and see when those have happened, and in written records of people that were here before us, and how often they happen. And then we can use that information to determine when it's probable that our next seismic event will happen. And so, for instance, in our area, we're kind of due for a big one, and we haven't had one. If we look at that kind of seismic gap, and I think it was about 10 years ago, the USGS put out a publication, said there's like a 90% probability that within the next 30 years we'll have 6 point something or higher in this area, I think, or a 7, somewhere around there. I'd have to look it up to be sure. But, you know, and so is it going to happen tomorrow? Is it going to happen 30 years from now? Is it going to happen 10 years from now? Is it going to happen 50 years from now? We can't be that precise, but we know that there is going to be a large earthquake in our future. It's happened in the past, and it's going to happen in the future. All right, so related hazards to earthquakes. Obviously, the ground moving. When there's an earthquake, things shake and tremble, and that causes problems. One of the problems that it causes is fire, and that's very, very common with earthquakes, especially in the past. You have this major shaking, and gas lines break, and now you have gas leaking, and electricity or some other means can cause that fire to get started. And so a lot of damage. The 1906 earthquake in San Francisco, much of the damage came from the fires associated with the earthquake. We also have ground failure. So in past units, we've talked about landslides and rock slides and things like that. Well, a lot of times those are triggered by an earthquake. We can have liquefaction. If you've ever been to the beach standing on super saturated sand and you kind of shake your feet, kind of move real fast up and down, you start sinking into the sand. That's an example of liquefaction. And it behaves kind of like quicksand, and buildings can tip or kind of sink down into the ground during an earthquake due to that. Permanent displacement of the land surface, so leaving fractures and scarps after the Ridgecrest earthquake. You could go over to the east side. There's some pretty cool drone footage. I'll see if I can find some of that and share it with you guys. You can see of an earthquake that happened in less than a year, very close to home. Anytime we have an earthquake, there's going to be lots of aftershocks. My mom lives up in Salt Lake City, and just, it was right about after we got out for the closure, I got a call early in the morning, and they had 5-something up there, and it scared her. And as I was trying to calm her and talk to her and explain that she's okay, but I also warned her that over the next few weeks, especially the next couple of days, there's going to be a lot more earthquakes, and to expect them and realize that that's totally normal. And sure enough, that same day they had probably about 4 or 5 in the high 3s, the mid 4s throughout the day. And over the weeks, they're still having them. Just the other day they had one. And so that's normal. When the earth moves, it moves a lot, but then it kind of settles, and it kind of is going back into place, and it continues to move. It's psychologically it's difficult, especially if it's a really big earthquake, because as soon as the earth starts moving again, your mind goes to, is it going to be another really big one? What's going on? And it can continue to cause more damage to already damaged buildings. Okay, I'm going to go ahead and stop here and finish up with part 3 here in a moment.